Right. So we're looking at we've learned the different types of energies before. We've learned about all these types of energies up here. Some of these we can calculate. Okay, so we can calculate kinetic energy, elastic energy. I mean, you can probably calculate a lot of them, but we're just going to look at some of the ones that we know that is in your GCSE. Okay, so we've got kinetic energy, elastic energy, thermal energy, electrical energy, gravitational energy. Those are the ones we're going to be looking at. Okay, and then we might also look at other related equations. So the symbols for kinetic for all the energies is going to be E, and then what we call a subscript. A subscript is when you have a little letter down here. So E, K. So K is the subscript. So we've got EK, that means kinetic energy, and that's equal to half times mass times the velocity squared. Okay? So in other words, let's do an example. Maybe we have something that has that the mass is perhaps equal to maybe 3 kilograms, and it's currently moving at maybe we can say 25 meters per second. So what I'd like you to do is try to calculate the kinetic energy of this object. Okay, so I'm going to pause the video and I'm going to give you the link to this whiteboard, and then I'll see how you get on with that. Right, so this doesn't look like it's right to me actually. So we've got 25 squared. If you do that on a calculator, but you can use your calculator in this exam. 25 squared is actually 625. Okay, so it's actually going to be, and if we can imagine that. So I would do it like this. So I would say that half times 3 times 25 squared, and I would group this together. Half times 3 is 1.5, and 25 squared, well, that's 625. Now, I don't really want to practice the mental arithmetic at the moment anyway, so what I would do, maybe what I can do here is, I'm going to just tap this into my calculator, and the answer is 937.5. Now the unit of energy is joules. Okay, yes. Oh, you knew that already. Good stuff. So that's our first calculation. All right, that's calculating kinetic energy. Let's go on to another example of an energy type you can calculate. I think we're a bit too big here as well, so I'm going to shrink that quite a bit, and maybe I'll group it too. So we'll do the next one. This is going to be kinetic energy. This is going to be gravitational energy. So I'll do an E again, a subscript, which is going to be G for gravitational. It looks a little bit like the symbol for example, but it means gravitational energy. And this time it's going to be equal to the mass. The mass times the strength of gravity. So different planets have different gravity. On Earth, so G on Earth. Have you heard about this? Do you know what the gravity is on Earth? No, okay. 9.81 newtons per kilogram. What this means is that every kilogram will experience a force of 9.81 newtons. That is how strong gravity is. Gravitational energy is going to be equal to the mass of the object multiplied by the strength of gravity multiplied by the height the object is at. Or we could say that maybe a better way to say this might be because it's really difficult to say how much gravitational energy something has, because when something falls, it could fall a little bit further. So it's better to say that the change, this triangle means change in, and a change in gravitational energy is equal to the mass times the gravitational field strength times the change in height. Okay, so that's probably a better way to think about it. So this triangle, it doesn't mean triangle times h, it just means triangle, it means a change in height. Okay, so this time I'm going to do a written question. So I'm going to pause the video and then I'll type it out and then we'll unpause it and have a look. Right, so yes, so this is going to calculate the amount of gravitational energy. Then what you do is you do the mass times the gravitational field strength, or the strength of the gravitational field, how strong gravity is, 5 times 9.81 times the height, which is 3 meters. So the amount of gravitational energy it has, the amount of gravitational energy it has is 147.15 joules. Okay, so if it was, let's imagine that we had a situation where the energy, all of the gravitational energy was turned into kinetic energy, then that would mean that we would start off with, let's say the object was falling, right? We've got this rock has got 147 147.15 joules, and that's gravitational energy. Yeah. Now, if that, and let's just squish that down here, and all of that is converted into kinetic energy, then it's going to have the same amount of kinetic energy transferred out. Okay, and that's only if there is no energy wasted. Remember what we looked at last time, that there is almost always going to be, so if you just want to follow me, then you can see what I'm pointing at here. So normally there was always going to, well, yes, I would say always, maybe almost always, probably always, there's energy wasted. And so we did this Sankey diagram before. Let's imagine a Sankey diagram for this situation. Maybe there is air resistance, or maybe there is friction as it is falling, and we can imagine what would the Sankey diagram look like for that. So I'm going to just put together, in fact, I think I'll keep the video going for this. We might start off with that. So we'll turn that into a rectangle, but then some of it is turned into kinetic energy. Fine. And the rest might be turned into thermal energy. So if I just make a second arrow and rotate it like that. And this is our Sankey diagram for this falling rock. Okay. So now in this case, it wouldn't necessarily be wouldn't be that. But let's say if it was actually made 100 joules of kinetic energy. This is going to be the thermal energy down here. Yeah, if you just follow me again. Can you work out how much thermal energy would be produced down here? Perfect. So if we know that because of the conservation of energy, let's just make a note of what the conservation of energy is. Try that again. Come on. Why wouldn't it let me type? Hang on a second. I may have to. So the conservation of energy. Conservation of energy. What is it? What is the conservation of energy? It is that no energy can be created or destroyed, it can only be transferred from one form to another. Okay, so if we look at this example here, we have started off with 147.15 joules of energy, and that is how much in total we have coming out the other end. And so that is the conservation of energy in action. Now, if we've got 100 joules of kinetic energy here, what we want to know now is it possible to work out how fast this rock must be falling? If it dropped 3 meters, then it's produced all this thermal energy, and it's also it's produced this kinetic energy too. But is it possible to work out how fast it would be? Well, I'm just going to see how you get on with this to start off with without my help. But it is a difficult question. I will tell you that you need to use the formula up here. You just want to follow me again. So we've got the object fallen. The object now has 100 joules of kinetic energy, and we know what the mass is. It's 5 kilograms, and we've got the formula up here: half times the mass times the velocity squared. So this is going to be using a little bit of algebra skills. What I would like you to do is find out what the final velocity is. Okay. Right. Well, that's good. That's your algebra skills are quite good. Okay, so that's going to really help you with your physics. A lot of people struggle with that question, and I think you did that quite well. You were very systematic. So let's get the final answer, because we need to get a final answer with a unit. Excellent. So you have no problem converting rearranging the equations. So if we know what the final kinetic energy will be, then we can work out the final velocity. So we've looked at the formulas for kinetic energy and for gravitational energy, and we converted between the two. And I did a little bit of revision of the Sankey diagrams over here. What are the types of energies will we do? Let's just first of all just label these ones here that we've just looked at. So we got gravitational energy. Yeah. So that one was this one down here. And then we had kinetic energy, which is this one over there. Okay, let's make the frame a bit wider. All right, so now we're going to be looking at elastic energy. So elastic energy, if anything, has the potential to spring back. Like imagine I squashed a spring. So I've got maybe like on a mouse trap or something, I've got a spring here. And then I'm going to squash it. So I'm going to squash it down from both ends like this. And now it's like that. So it's a bit more squashed, okay? Okay, so I'll just let you undo for a moment. So this bit of the bit that's been squashed, we can call that well, it's often referred to as extension, but of course it's not being stretched, it's not being extended. It could be squashed or stretched. So what we're just going to call it is x. So x is the amount it has been stretched, or because it could have been. So this one's been squashed, but it could have been stretched like this. So now this extra bit here would be x. Okay. The distance it is squashed or the distance it is stretched, we can call x. Okay. And sometimes it's called E. So sometimes X could be the same. Just instead of writing X, they might write E. But there's not an official kind of way for it. Okay. So how do we work out elastic energy? Well, elastic energy, which is going to be the E subscript E, is equal to half, very similar to kinetic energy, half times this K value multiplied by X squared. Now, the K value is what we call the spring constant. Now, the spring constant is basically how difficult it is to stretch or squash the spring. We can imagine some springs can be very difficult to press, and some of them are very easy to press. So a high spring constant will make it very difficult to press. So if we had, if we had a high spring constant and I squashed it quite a bit, then that spring has a lot of elastic energy. So I'm not going to do an example of that because I think you did the calculations quite well. I'm just going to introduce the different formulas at the moment. So next one we're going to look at is electrical energy. Now we can see a problem because what would be the symbol for electrical energy? I guess it would be E subscript E again, but that's what elastic energy is. So these aren't official terms, okay? So what we're going to call this one is, we're going to call this one E, and then subscript E, L, E, okay? And to calculate electrical energy, we do is equal to voltage times current times the amount of time. Let's imagine that we had a motor going. So I'll just get a picture of a motor. So hopefully this is an electrical motor, but it looks like it is, to be honest, but doesn't matter if it is or not. We're going to presume it is. This is connected to a battery. Like this. And we've got I need to put an ammeter in it. Oh, that's a bit messy. So I can measure the current with the ammeter, and then I can put a voltmeter across it like this. And I can measure the voltage with my voltmeter. And then I can have a stopwatch that's not very good, is it? A stopwatch to measure the time. That's supposed to be a stopwatch, okay? Okay, with a little string. Anyway, so I could work out how much electrical energy was given into this motor by timesing the voltage, by the current, and then by how many seconds. That's electrical energy. So what have we got? We've got kinetic, gravitational, elastic, and now electrical energy. There is another one, and that is thermal energy. Actually, we want, try that again, a rectangle. So thermal energy. I've just put elastic here, but of course it's elastic energy. So thermal energy, there's a lot of symbols here, so I'll do a key in a moment so we can see what all these V, I, T, K, X and all that is. But let's just write these down first. So the thermal energy, which I'll do E subscript T, is equal to the mass of an object. Let's imagine we are heating up an object, and we want to know how much heat can this object, how does the heat relate to the temperature change? Well, you multiply it by the mass, multiplied by something called the specific heat capacity. And this is just basically how easy or difficult is it to heat something up. Specific heat capacity. And then you multiply it by the change in temperature. Okay. We're going to have to leave our Zoom meeting and come back soon, but I'll just finish this little summary of energy types. We've got 5 types there. I think that might be all of them. I'm just going to have a look to see if I've missed any out. We've done gravitational, we've done elastic, we've done kinetic, thermal, and so we've done that's all the ones that you'll need to know. So these are all the different energy types, and then what I'll do is I'll extend the whiteboard a little bit further, and then we'll say related calculations. So the related calculations are going to be basically power. What is power? Well, let's think about what we understand about power. Imagine we had 2 cars. So I'm going to get like a powerful car and a car that doesn't look very powerful. So there's no doubt that this, we could, just from looking at it, we would say fairly likely that this car is. Oh, that's okay. So it's fairly likely that this car is. Oh, hang on. Okay. So it's fairly likely that this car is powerful, and or let's just call it more powerful. More powerful. So what does powerful mean? What can this car do that this car can't do? We can't say it can do more work because it just depends on how much energy you give it. If you give this one more petrol, then this can do more work. It's basically, or use more energy. It's basically to do with how quickly it can use the energy. So the power is equal to. I'm just going to get a thicker pen. The power is equal to the amount of energy transferred divided by the time taken. Okay? And power is not measured in joules because it's not energy. It's how quickly the energy is used. So the unit for power is watts, and that's a capital W. And then time would be in seconds, and we know that energy is in joules. Another related formula with energy is work done. So I'll get an image for this one. Okay, so this is let's imagine this person is pushing something, and there's a certain distance he's going to push it for. Then the amount of work done. Well, first of all, what is work done? Work done is the amount of energy used to do something. And how do I calculate it? Well, the symbol for work is capital W, and that's equal to the force multiplied by the distance traveled. Okay. Now those are pretty much all of the. I guess there's one. Actually, there would be one more formula, and that's relating to this example up here. Let's pretend that we are trying to. Let's pretend that this is the useful energy. So we'll make this one green, and this is the wasted energy. We'll make this one red. And this was the useful energy. I think I used blue the input energy. So I'll make this one blue. So what this is efficiency. So efficiency. Oh dear. So efficiency is how good is something at doing what it's trying to do. And we're going to pretend that this rock is trying to produce kinetic energy. So how good is it at doing that? We need it in a percentage. It's usually in a percentage. It doesn't actually have to be in a percentage, but it doesn't have any other units. It's either percentage or it's no units. So how would you work this out? Well, it basically, I think what I might do is do it like this. So I'll turn off that and I'll say equals, and actually I'm going to turn off the background. So that's equal to the the useful energy output. No, I won't do that. And I'm just going to do an underline here. And that's divided by the total energy input. You can see why it would have no units, because it's going to be joules at the bottom and joules at the top. So the joules will cancel out. And then to turn into a percentage, we need to multiply it by 100%. Okay. So we've got, how many formulae have we looked at today? We've got 1, 2, 3, 4, 5, 6, 7, and I think that was 8. So let's use a pink highlighter to highlight the different formulae now. So we've got, and I think it looks like the symbol disappeared there somehow. Let's rewrite that one. Yeah, great stuff. Okay, I'll let you highlight that then. Do you want to highlight the formulae in pink, and I will rewrite the, make sure that they're all written properly. It looks to me like they're all there. Yeah, okay. I'm going to stop the video and just save that. Do you want me to draw it? Okay, I'll just stop the video and I'll save it and put it there. Okay.